GISP Unofficial Study Guide, Section 3, Cartography and Visualization. Section 301, Understanding of Graphic Representation Techniques and Implications. A thematic map is a type of map especially designed to show a particular theme connected with a specific geographic area. A choropleth map. In a choropleth map, areas are shaded according to a prearranged key. Each shading or color type represents a range of values. A proportional symbol map. Symbols are drawn proportional in size to the size of the variable being represented. Isarithmic or isopleth map. An isopleth map has lines of equal value that are drawn, such as contour lines, or ranges of similar values that are filled with similar colors or patterns. A dot map. A dot map shows distribution of phenomena where values and locations are known. A dot is placed where the location of a variable is. A daisymmetric map is an alternative to a choropleth map. In a daisymmetric map, ancillary information is used to model internal distribution of the phenomena. Multivariate displays. A multivariate display puts more than two sets of data on one map. For example, a single map showing population density, annual rainfall, and cancer rates. Web mapping. Web mapping is the process of using maps delivered by GIS. Web maps are both served and consumed. A thematic map. A thematic map is a type of map that portrays the geographic pattern of a particular subject matter, or theme, in a geographic area. This usually involves the use of map symbols to visualize selected properties of geographic features that are not naturally visible, such as temperature, language, or population. Thematic maps contrast with general reference maps, which focus on the location more than the properties of a diverse set of physical features, such as rivers, roads, or buildings. Alternative names have been suggested for thematic maps, such as special subject or special purpose maps, statistical maps, or distribution maps, but these have generally fallen out of usage. Thematic mapping is closely allied with the field of geovisualization. Choropleth maps. Choropleth maps are maps where areas are shaded according to a prearranged key. Each shading or color type represents a range of values. Isopleth maps. Isopleth maps differ from choropleth maps in that the data is not grouped to a predefined unit. Isopleth maps can take two forms. They can have lines of equal value that are drawn such that all values on one side are higher than the isoline value and all values on the other side are lower. Or, an isopleth map can have ranges of similar value that are filled with similar colors or patterns. Proportional symbol maps. With proportional symbol maps, symbols, most often circles, are drawn proportional in size to the size of the variable being represented. Dot maps. Dot maps are used to show the distribution of phenomena where values and location are known. Dot maps create a visual impression of density by placing a dot or some other symbol in the approximate location of the variable being mapped. Web mapping. Web mapping, or online mapping, is the process of using maps, usually created through geographic information systems on the Internet. A web map or online map is both served and consumed. Thus, web mapping is more than just web cartography. It is a service where consumers may choose what the map will show. Section 302. Understanding of map design principles and essential map elements. Map layout elements include title, map, legend, map scale, supporting media, north arrow, and metadata. Metadata includes sources, currency of information, projection, copyright, and authorship. Symbols represent things on a map. Map accuracy is difficult to assess. All maps show a selective view of reality. Instead of assessing map accuracy, one could assess if the map is appropriate for its intended purpose. Map scale, 1 to 100. 1 inch represents 100 inches in the real world. A large map scale is more zoomed in and shows more detail than a small map scale, which is more zoomed out. Symbolization variables can include size, shape, orientation, pattern, hue, and value. Quantitative information can include the size of the point or the thickness of a line, the value, the shade of the color such as dark red or light red. Qualitative information can include the shape. 4 points could have different symbols. The pattern, lines having different styles such as dashed lines. And the hue, which can make different colors such as red and blue. Typography is the design of the text, the point size, the line length, and the typefaces. Map scales. A verbal scale expresses in words a relationship between a map distance and a ground distance. For example, 1 inch equals 16 miles. A visual scale is a graphic scale or bar scale. A representative scale is a representative fraction or ratio scale, such as 1 to 24,000, or 1 inch equals 24,000 inches. Absolute scale is a system of measurement that begins at a minimum or 0 point and progresses only in one direction. Relative scale, or arbitrary, begins at some point selected by a person and can progress in both directions. Display versus data. The data is built at a certain scale or accuracy, but once the data is displayed in any other format than the one it was made for, the scale gets warped. Example: a map made as 9 inches by 10 inches that is then scaled down and printed in a newspaper. Large scale. A large scale is when there's a small ratio between map units and ground units. Small scale. Small scale is when there is a large ratio between map units and ground units. Cartographic design. Cartographic design is the process of creating a map to represent geographic information. Effective cartographic design employs general principles and techniques common to any form of design, along with theory and techniques specific to cartography. There are 6 definable elements that separate a good map from a bad map: clarity, order, balance, contrast, unity, and harmony. Clarity is when the map focuses on its purpose with as little distraction as possible. Order is when the elements of the map are organized to guide the map reader to accomplish the intended purpose. Balance is when the elements are distributed to give the map a feeling of evenness. Contrast is when important elements stand out clearly against less important ones. Unity is when the various elements come together to make the map appear as a single coherent whole. Harmony is when the elements all seem to fit together naturally. Maps can be categorized into a few types of purpose: descriptive, narrative, rhetorical or prescriptive, and exploratory. Descriptive maps tend to have a broad purpose, showing the features on the landscape as accurately as possible. Narrative maps have a specific message to convey. Rhetorical or prescriptive maps attempt to convince map readers to have a particular opinion. Exploratory maps typically do not have a particular message because the cartographer is using the map to explore the geographic data and discover patterns. Map composition. A map typically consists of multiple layers or themes that convey the purpose of the map. Composition is the technique of designing the different objects and layers in the map to be aesthetically attractive and useful, and to work together effectively as a whole. There are 2 general types of maps. Maps that give general information about locations of features are reference maps. Maps in road atlases are an example of reference maps, as are topographic maps. Those that show the distribution of a specific topic are thematic or statistical maps. A map showing population distribution by county is a thematic map. General mapping concepts. All maps are representations. It is not possible to show features at their actual size, nor is it possible to show full detail. A map is a model of the Earth at a reduced scale. Some maps, such as diagrams of chromosomes or atoms, are in large scale, but generally, maps are smaller than the things they represent. Because features cannot be shown at their true size, they must be generalized. Some details are omitted to make the most important characteristics of a feature more apparent. In addition, 3-dimensional objects have been flattened for 2-dimensional display. The transfer of features from 3 dimensions to 2 involves the use of a map projection. When you look at a map, you don't see real features like buildings or people, you see symbols that represent these things. Symbols should be easily understood by the map reader. Map projections. A map projection is a set of rules for transforming features from the three-dimensional Earth onto a two-dimensional display. No flat representation of the Earth can be completely accurate, so many different projections have been developed, and each is suited to a particular purpose. Map projections differ in the way they handle four properties: area, angles, distance, and direction. No projection can preserve all four simultaneously, although some combinations can be preserved, such as area and direction. No projection can preserve both area and angles, however. The map maker must decide which property is most important and choose a projection based on that. An equal area projection preserves area, and are also called equivalent projections. Most thematic maps should use an equal area projection. The Albers equal area conic projection is commonly used for the United States. Common projections for the world are the equal area cylindrical and sinusoidal. Conformal projections preserve angles and are used for navigational charts and weather maps. Shape is preserved for small areas, but the shape of a large area, such as a continent, will be significantly distorted. Common conformal projections are the Lambert conformal conic and the Mercator projection. Equidistant projections preserve distances, but no projection can preserve distances from all points to all other points. Instead, distance can be held true from one point to all other points, or from several points to all other points. Several projections have the property of equidistant. Azimuthal projections preserve direction from one point to all other points. This property can be combined with any of the other three. Thus, it is possible to have an equal area azimuthal projection, such as Lambert, or an equidistant azimuthal projection. Compromise. Compromise projections minimize overall distortion, but preserve none of the four properties. The Robinson projection, for example, is neither equal area nor conformal, but is aesthetically pleasing and useful for general mapping. Map generalization. Map generalization is an umbrella term for several processes, all intended to remove unnecessary detail. Because maps cannot show everything, the map maker must select which features to show and which to omit. Features may need to be simplified to be legible at a smaller scale. In many cases, data need to be classified, divided into groups of similar values. Finally, symbols must be chosen to represent features on the map. Classification. Common classification schemes include equal range, quantiles, standard deviation, and natural breaks. Equal range classification. Equal distance between class breaks. Useful when a diagram of data distribution is rectangular and enumeration areas are of equal size. Quantile classification is when an equal number of observations is in each class. Class intervals can be dramatically different in size. Standard deviation classification is when class breaks are based on the distance of standard deviation from the mean. It is useful if diagram of data distribution is a normal curve. This is good for showing deviation from the mean. Natural breaks classification is when class breaks conform to gaps in data distribution. Visual variables. There are several characteristics of a symbol that can be manipulated, which are often referred to as visual variables. These are size, shape, orientation, pattern, hue, and value. Not all variables apply equally well to different kinds of phenomena. Also, not all variables apply equally well to different types of data. Shape and pattern can be used for qualitative data, but not quantitative data. Size and value can be used for quantitative data, but not for qualitative data. Qualitative data is best represented by shape, pattern, and hue. Quantitative data is best represented by size and value. Map accuracy. Map accuracy depends on several factors, such as positional accuracy, logical consistency within the dataset, and the age of the data. Six elements of map accuracy include positional accuracy, attribute accuracy, resolution, logical consistency, currency, and completeness. The first four elements of map accuracy concern the individual elements of a dataset. The first four elements of map accuracy include positional accuracy, attribute accuracy, resolution, and logical consistency. The remaining two items concern the dataset as a whole. The remaining two items are currency and completeness. Positional accuracy. Positional accuracy concerns the measurement of feature locations. The positional accuracy of a GIS database depends on the reliability of source data and the ways it has been manipulated. Positional accuracy can be evaluated by taking measurements from randomly selected features in your database and comparing them to the position of those features in a database known to be reliable. Attribute accuracy. Attribute accuracy concerns the measurement of the characteristics of a feature and can be greatly affected by data classification. Resolution. Resolution refers to the size of the smallest feature in the dataset that can be discerned. The term minimum mapping unit is also used to describe resolution. Logical consistency. Logical consistency refers to the relationships between data items and whether or not the relationships make sense. Currency. The world is a dynamic place. Goods are bought and sold, people are born and die, and even the continents are moving. However, some changes occur more quickly than others. Thus, some types of information change quickly. You have to decide how current the data needs to be useful. So currency is how current the data is. Completeness. Completeness can describe both the areal extent of a dataset and the level of detail in the data classification. Six elements of map accuracy include positional accuracy, attribute accuracy, resolution, logical consistency, currency, and completeness. Map composition. To communicate its message effectively, your map needs context: a title, a legend, a scale bar. Thus, the map is really just one element in the page layout. Some of the basic elements of map layout design include balance, hierarchy, figure-ground relationships, and contrast. Balance refers to the arrangement of elements within the overall composition and whether these elements appear stable or unsettled. Hierarchy refers to the perceived importance of map elements. The most important information on a map should have more visual impact than the background information. The figure-ground relationship is part of the visual hierarchy. Objects that appear to stand out are figures, while the background information is the ground. Important information such as symbols should appear as figure, while the context information should appear as ground. Contrast refers to the degree to which different elements are distinguishable from one another. Objects that stand out from their background have high contrast, while objects that seem to blend together have low contrast. Contrast, therefore, is useful for establishing figure-ground relationships. Contrast can be achieved through variations in color, value, pattern, line weight, or type size. The basic elements of layout design include balance, hierarchy, figure-ground relationships, and contrast. Typography. Typography is defined as the art or process of specifying, arranging, and designing type. Typography describes elements of the type itself, including font, color, size, typeface, line length, and leading, or line spacing. In cartographic design, a variety of text material is found in maps to meet different purposes, like for titles, labels, legends, annotations, etc. In this sense, typography becomes a symbol in its own right and an important aspect in producing a quality map. Absolute scale. There is no single definition of an absolute scale. In statistics and measurement theory, it is simply a ratio scale in which the unit of measurement is fixed and values are obtained by counting. Absolute scale differs from an arbitrary or relative scale, which begins at some point selected by a person and can progress in both directions. An absolute scale begins at a natural minimum, leaving only one direction with which to progress. An absolute scale can only be applied to measurements in which a true minimum is known. Time, for example, which does not have a clearly known beginning, is measured on a relative scale, with an arbitrary 0 point, such as the conventional date of birth. Absolute scales are used when precise values are needed in comparison to a natural, unchanging 0 point. Measurements of length, area, and volume are inherently absolute. although measurements of distance are often based on an arbitrary starting point. Section 303, Understanding of Surface Interpretation and Representation. There's not much in this section in this study guide. It just says be able to read an aerial map and interpret features, and be able to decide how a geographic feature should be represented in a GIS. Section 304, Understanding of 2D and 3D Visualization. 3D mapping brings in a z-value. This is typically elevation data. A contour line, aka an isoline, isopleth, or isorhythm, is a function of two variables, is a curve along which the function has a constant value. A contour line joins points of equal value on a line. A contour interval is the difference in elevation between successive contour lines. An index contour is when the contour that is thicker and typically labeled. ISO means equal, and this means equal distances between lines. 3D mapping has also included building modeling. A contour line, also known as an isoline, isopleth, isoquant, or isorhythm of a function of two variables, is a curve along which the function has a constant value, so the curve joins points of equal value. In cartography, a contour line, also called a contour, joins points of equal elevation or height above a given level, such as mean sea level. A contour map is a map illustrated with contour lines, for example, a topographic map. A contour interval of a contour map is the difference in elevation between successive contour lines. The gradient of the function is always perpendicular to the contour lines. When the lines are close together, the magnitude of the gradient is large. The variation is steep. A level set is a generalization of a contour line for functions of any number of variables.